Welcome to EDU World Space.
Problem number 54. You can see the figure on the left. We are asked to determine the electric field Z above a large plane of charge. Taking advantage of what we proved in example 21-11 of the textbook. So we're advised to divide the plane into long narrow strips, let's say of width dy, as you can see here, and length L. And we can write that then dq is going to be equal to the surface charge distribution times L dy, being the area, right? So if this dy is really, really narrow, then we can write the charge per unit length as, lambda as dq over L, right? So then if we plug in dq here, sigma L dy over L, then lambda is going to be sigma dy, right? So let's remember from the example 21-11, we have the electric field differential of it as lambda over 2 pi epsilon naught y squared plus z squared, adjusting our dimensions for this problem. So what we have is lambda is sigma dy over 2 pi epsilon naught y squared plus z squared then, right? So if we look at the figure, take any arbitrary point charge within this strip, you can see that the electric field that it generates is going to have two components, right? The z component and y component. But across this, imagine another strip here, purely symmetrical to the other one, right? And it's going to generate a dE that goes in the opposite direction. So you can see how the horizontals are actually going to cancel out, and the only component that we're going to left with is the z component. So then it's wise to calculate the z component of the electric field. So then looking at the angle, it's going to be dE times the cosine, right? The angle is here, cosine theta. So what is this cosine theta? This is also theta, right? So the cosine theta would be adjacent, which is z, over hypotenuse. Hypotenuse being this r, and that equals to what? Z squared plus y squared, z squared plus y squared, the square root of this, right? So then we can substitute for dE as sigma dy over 2 pi epsilon naught y squared z squared. Let me write it in this form rather than writing it in the square root. So times cosine being z over z squared plus y squared 1/2. From here, then what we have is sigma z dy over 2 pi epsilon naught y squared plus z squared, right? Now what we're going to do then, we're going to take the integral. In order to get to EZ, we're going to take the integral of sigma z over 2 pi epsilon naught, right? So we have dy and y squared plus z squared in denominator, right? Well, we're assuming that this is a very large plane, so we're going to integrate it from negative infinity to infinity. And if we look up this antiderivative, it is 2 epsilon naught. It is 1 over z inverse of tangent of y over z. So we're going to evaluate this from negative to positive infinity. Again, since z has nothing to do with these limits, it can cancel this one out. So we have sigma over 2 pi epsilon naught here, and then inverse of tangent, what do we have? Infinity, right? Minus inverse of tangent at negative infinity. As you know, the first term is going to give us pi over 2 minus negative pi over 2, right? So then what we have is sigma over 2 pi epsilon naught, pi over 2 plus pi over 2. So this makes a pi. This pi is going to cancel out the pi in denominator. And ta-da, we have sigma over 2 epsilon naught for a plane charge distribution. We could get to the same answer using Gauss's law.